All right, so we're going to take a look at 6.3 part 2. Okay, this is the second part. We're still not going to look at combining multiple transformations together. We're going to look at them isolated. And today we're going to look at the stretches. Horizontal stretch or compression and vertical stretch or compression. When we do stretching, what kind of arithmetic is involved? Like shifting, it's one kind. Stretching is something else. Yep?
Multiplication.
Right. Everything today is going to be multiplication. Whether it's multiplying on the inside or the outside, that'll control whether it's horizontal or vertical. All right. So one term we did not talk about yesterday was called the amplitude. Okay, the amplitude measures the height of a sine or a cosine wave. For all of the sine and cosine functions we did yesterday, every single one of them had the same amplitude. Does anybody remember what the amplitude was for all the graphs yesterday? And it's the distance from that center to the peak. Yeah? 1. 1. The amplitude of every function we did yesterday is 1. Sliding up and down doesn't change the amplitude because you're always measuring from the center line to the peak. Right? And shifting left and right does not change the amplitude. Shifting up or down could change the maximum value. That's different. That function has a higher maximum y value now, but it's still, if you put the center line in there, it still has the same amplitude as the one below it. Okay. Any question on the difference between like the maximum value versus the amplitude? All right. So another thing about amplitude is the amplitude measures height. So what kind of number do you think that means the amplitude always has to be? Yeah.
Y value.
Well, it is measuring a vertical distance, but yeah, it has to be a positive number. Okay, you would never have a negative number for the amplitude because it's a distance. When we are doing an amplitude change, this would be the third transformation that would be in the order we would do them in. So that's why I'm using the letter C to represent it. It's not that important today that you know it's the third one, but the next lesson after midterms, we're going to combine all the stretching and shifting together, and then you need to know the order. But it's the same order we've been doing all year. Okay. So multiplying by a number in front is what causes an amplitude change. So if you want to find just the amplitude of a function, you take the absolute value of the number in front. So I'm not saying that if there is a negative here, it doesn't have an effect on the graph. The negative does. The negative causes a flip. But the negative has nothing to do with the amplitude. Okay. So as an example, if we sketch, let's just do like sine x and negative 1 sine x. Both of those numbers have both of those graphs have an amplitude of 1. There is a number being multiplied in front of the bottom one. And if I take the absolute value of that number, it will tell me the amplitude, which is 1. Okay. So you can see it causes a flip, but it doesn't change the amplitude. Okay, so the negative has no effect on amplitude, just on when you do the sketch. So any question why a negative doesn't affect the amplitude? Okay. So yeah, absolute value of the number in front, that is your amplitude. So what if I had like 3 cosine x, and I just asked what is the amplitude? What would you say? Yep, 3. Yep, 3 is the amplitude. How about y equals negative 3 cosine x? What's the amplitude of that? Yep, It's also 3. There's a flip in there, so when we sketch it, we got to take the negative into account. But if it's asking for the amplitude, the negative does not make a difference. Okay, it just causes a flip. So an amplitude change is going to stretch or compress the graph along the y-axis. So as an example, if this was your original, a change in an amplitude could be something like this. That would be a stretch. Right? It could also compress. That would be a compression. I think I kind of already mentioned it, but if the black was the original sound, how do you think the red sound would compare to the black sound? Yeah?
It would be much louder.
Yes, it would be louder. So stretching and compressing vertically affects the volume. Yep. If this wave represented an electromagnetic waves don't have volume. That's like, light. Light doesn't have volume. But the way we perceive intensity for an electromagnetic wave for light would be like brightness. So if that was a light wave, the red wave would be a brighter light. The blue wave would be a darker light. Or if it was an X-ray, it would be a stronger X-ray or a weaker X-ray. Right? But that's what stretching and compressing vertically does. It affects the intensity. Right, so let's try a couple more finding the amplitude. Well, we already did this one. I think I did that one up above. How about that one? What's going to be the amplitude of that? Yeah?
4/3.
Yeah, 4/3. There's all kinds of other things happening. There's a phase shift and there's a vertical shift, but those two things have nothing to do with amplitude. Right? This +6 would affect the maximum value. That would be a different question. If I said to you, what's the highest y value this graph ever hits? The +6 would be important. Right? But just for amplitude, no, it's not important. How about -2 sine x? Amplitude there?
2.
Just 2. Yep. Okay. With the other trig functions, we don't talk about amplitude. Because amplitude measures how high, basically, the wave goes at the center line. Well, if you look at the graph of tangent, it goes up and down forever. So what would you say? Infinite amplitude? It doesn't make sense. So sine and cosine are really the only two trig functions that have a reference to amplitude. Right? And I can play it. It's not overly interesting, but when you stretch and compress it, it just changes the volume. Right, so let me see if I can. Yeah, I think I can do it from here. Right? And as I compress it, it gets quieter. So that's a change in amplitude. All right, so the first thing we have to do is figure out what is going to stay the same and what's going to change in our table. If we are stretching and compressing vertically, which values are not affected? Yeah, right, the x's. Whenever the x's aren't affected, that's great because the x's are the more complicated ones to work with. Those are all the fractions with pi. Because the x's are staying the same, we can copy them down from the table, and they are the same for sine and cosine. Can someone remind me, what are those x values again? The 5 that we always use? Yeah?
0, pi divided by 2, pi, 3 pi over 2, and 2 pi.
2 pi. Yep. So for an amplitude change, those are going to be our x values. The only way that would change is if we did like multiple transformations at the same time, but we're not doing that today. Okay, so all our amplitude changes will have those x values. And to find the new y values, just take the old y values and multiply by c. Notice it does not say absolute value of c. You have to use whatever number is in front because the negative has a big impact on what the graph looks like. So if c is a negative, use the negative. So essentially with amplitude changes, I guess we are kind of doing two at the same time. We can do a flip with an amplitude change. But we can still handle that all in one step. Just multiply the old y values by the number in front, and it handles both at the same time. All right, so let's try this one. Okay, so first thing we want to do is make sure we know what kind of transformation it is. So Dex, what kind of transformation is that?
Like a stretch.
Yep, and what kind of stretch? Which direction?
Like a vertical stretch.
Right, it's a vertical stretch because we're multiplying by a number. That means it's a stretch, and it's outside of the argument. Okay, that's your argument, and it's not inside there. We are going to do inside there, but that's next. Okay, so we know it's a vertical stretch. Nick, which column here is going to stay the same?
X.
X, we just said what those were. Okay, I know all my y values are going to change, but for reference, I'll put the original on the outside. Holly, what are my original y values for the cycle of cosine that we graph?
1, 0, -1, 0, 1.
Yep. And for those that were absent yesterday, I don't want you to think these are the only y values and the only x values. This graph goes on forever. All that we're doing is we're trying to sketch one section. That's what our goal is. Okay. And the section that we usually sketch is the first positive section. Okay. All right, so we've got our x's, we've got our old y's. How are we going to get the new y values?
You're gonna multiply that, right?
Right, just take the old y values and multiply by 3. Okay, so we're going to get 3, 0, -3, 0, and 3. Those are your new y values. Okay, so there's our table. Any questions on that? Now, when we sketch it, depending on how big of an amplitude change you make, you'd have to use a bigger and bigger piece of graph paper. So to avoid that, I'm going to scale my y-axis. The way I'm going to scale it is I'm going to go by 3s. So essentially, every graph that I do that's an amplitude change looks the same. And the reason it looks the same is because I change the scale. Right? That way, I don't have to actually draw something 3 times or 20 or 50 times as large. Just change my scale. X values, I don't have to change anything. Right? And now I'll just graph all my points. So I've got 3, 0, -3, 0, 3. 0, -3, 0, and 3. And there's your sketch. If I had to do the graph of 5 cosine x, the only thing I would change here would be to make that a 5 and make that a -5. But I could keep the picture exactly the same because I changed my scale. You don't have to change your scale that way, but it just makes it easier so you don't need a gigantic piece of graph paper. All right. Any questions on the sketch? Okay, so that's called an amplitude change, or putting it in terms of what we've used before, a vertical stretch. All right, let's look at this one. 1/2 sine x. Okay, again, it's multiplying by a number in front, so we know it's a stretch. Because it's outside of the argument, we know it's vertical. Okay, vertical stretch. X's are staying the same. Lucas, can you remind me what those X's are again?
Let me see. I think it's 0. Oh, no. Oh yeah. Pi over 2. Pi. 3 pi over 2. And then 2 pi.
2 pi. So those are good. You know those are staying the same. All the y's are going to change. Can somebody else give me my original y values? Yep. 0, 1, 0, negative 1, 0. And how are all of those going to change? What are we going to have to do to all of them? Yep.
Multiplied by a half.
Right, they're all going to be multiplied by a half, divided by 2, however you want to think of it. So we're going to get 0, 1 half, 0, negative a half, and 0. So that's your table. Questions on how I got that table? And now we're going to use that table to sketch 1 cycle, and then if you had to sketch 2 or 3 cycles, you could just copy and paste your picture over and over to get as many cycles as you want. All right. I'm going to do the same thing I did last time. I'm going to scale my y-axis, so if this was graph paper, all my points would be on nice intersections of the graph paper lines. Okay, label your x's. And graph your points. So we're at 0, 0. Pi over 2, we're at 1 half. Pi, we are back at 0. 3 pi over 2, that's the lowest that it goes. And 2 pi, back at 0. And there's your sketch. Questions on the sketch? Does anybody remember what the word that I used to describe how that curvature and that curvature compare? It's called the something of the curve. It was just something I said verbally. It's not something I wrote down. Yeah? Yeah, exactly, the concavity. This red section is what we call concave down because water would fall out. The blue section is concave up. And in calculus, you learn how to find all these changing concavity points using calculus. All right, try one more this type. Okay, what's happening in this one? Yeah.
It's being reflected.
Can you be more specific?
It's being reflected over the y-axis.
Um,
Oh, no, x-axis.
it's a vertical reflection, so that would mean it's over the
x-axis.
x-axis. Yes. So technically speaking, it is not an amplitude change, but we can still handle the arithmetic the same way. It's like you're multiplying by -1 in front. Okay. So x's are going to stay the same. Original y values, we already did those a couple problems ago. 1, 0, negative 1, 0, 1. And my new y values, they're just all going to change sign. That's all that's going to happen. So negative 1, 0, 1, 0, negative 1. So the normal section of cosine that we sketch kind of has like a U shape to it. Well, this is going to be flipped over. So it's going to be more like an N shape. That's the general look. Now I should label whatever I need to for my axes. Y's I don't need to label. If you want to, you can, but it's not necessary. X's you should label because you are not going by ones. Okay. If that's how you did your sketch, I would assume that like this is the coordinate 1, 0, 2, 1, 3, 0, and so on. Okay, so let's just label those with what we want. Now we know we're not going by ones. We're going by pi over 2's, which means we're going by what in degrees? Each tick mark is worth how much? Yeah? 90. In fact, every single graph that we've done up until now, all 3 transformations I've taught you, each tick mark has been worth 90. When we start talking about changing the period length, they're no longer going to be worth 90. Okay? And that's the last thing we'll do. Okay. Any questions on that one? All right, so we've done both shifts. We've done the vertical stretch. The last one is the horizontal stretch. Like some of the other transformations, they do use a different name. They call it a period change. What is the length of the period, or the length of the cycle, from here to there, in every problem we've done up until now? To travel one cycle, you have to go how much? Yeah.
2 pi
2 pi
in radians.
2 pi in radians, or yeah,
360 degrees.
360 degrees. Okay. It takes 360 degrees to go through one full cycle of sine or cosine, if you don't change the period. Okay. Now we're going to look at changing the period. Okay, so standard period, we just said that is 2 pi radians. This transformation, when we start doing all 4 of them, well, actually all 6 of them, if you include the stretches is 2, the shifts is 2, and the reflections is 2, there's really 6. Once we do all 6, this would be the second one that we would handle in order. That's why I use the letter B. So it is a stretch, and it is a stretch horizontally. We're generally going to focus on examples where B is greater than 0. We could do less than 0. It would just cause a horizontal reflection. But for these particular graphs, we're not going to worry about horizontal reflections. So now if I graph, let's do, just say the original, sine x, and then I do sine 5x. What do you think the 5 is, what's going to be the effect of the 5? Yeah?
It's gonna stretch it vertically or horizontally.
You think it's going to stretch
by
it
a factor
horizontally?
of 5.
So if the period was 2 pi, what do you think the new period would be?
10 pi.
So you think it's going to stretch out
Yes.
5 times as much? Okay, if it did stretch out 5 times
Actually,
as much,
no, it would shrink.
you think it's going to shrink?
Yeah. It would.
By how much?
10 pi. Or no, wait, 5.
Yeah, it's going to shrink by a factor of 5. That is what's going to happen. Okay, it's going to compress. So what do you think the new period length would be? If it's going to compress by a factor of 5. Yeah?
2/5. You're 2/5 pi.
Yeah, 2/5 pi, 2 pi over 5. Yeah, it's gonna compress it. So if I hit graph, there's your original. And what you're gonna see now is the red one is gonna have 5 times as many cycles in a given section. And I can easily show you that if I just let that finish. And we'll focus on one cycle of the blue one, and I'll show you how you have 5 of the red one now. Just take that there. All right, so I'll focus on the section from there to there. That is one section of the blue wave. That's the original. Now count how many cycles you have of the red one. 1, 2, 3, 4, 5. So you're now getting 5 times as many cycles in the same space, which means the period length is 1/5 of 2 pi. If you wanted to stretch it, you would have to do a number that's not a 5. What kind of number could we do that would stretch the graph? Yep.
1/2.
Yeah, we could do a 1/2 or 0.5. Now the red one is going to be twice as long as the blue one. It's going to be stretched out. So for every 1 red cycle, now you're getting 2 blue. Okay. And what do you think the period length of this red one would be if it's been stretched out twice as much of the original? Yeah.
4 pi.
It would be 4 pi. Yep. So that's one thing that we are going to figure out. When I give you a graph, I might just ask a question and say, what is the period of the following? You don't even have to sketch it. I just ask you, what is the new period? And we'll do sketching after. Right? And now let's just take a quick look at what that sounds like. All right, so when we stretch and compress it horizontally, it's not going to change the volume. What else do you think I can change about the sound besides the volume? Yeah?
Frequency or how low or high it is.
Right, I can change the frequency of it. Right, so let me do that. Okay, so that's 1,000 hertz. All right, so we looked at that. So period changes, we saw that they're going to stretch and compress the graph along the x-axis. For sound, it changes the frequency. If it was an electromagnetic wave, it changes the type of wave. And by type, I mean from like X-ray to gamma ray, or it would shift the color of a light wave, maybe from red to green or green to blue. Okay. And depending on the number that you put, it'll either stretch or compress. Horizontal is always backwards, so the bigger you make the number, the more compression you get. The smaller you make the number, closer to 0, the more stretched it gets. So sometimes what they want us to do is just figure out what is the new period length. To figure out the new period, all you have to do is take the original period and divide by whatever you're stretching or compressing by. Right? If you put a 2 inside here, remember what a 2 is going to do. A 2 is going to compress it. How much is it going to compress it by? Double. So you're going to get double the amount of waves in the same period, which means the cycle length was cut in half. So that's why you divide by b. To get the new period, you don't multiply by b. If you put in like 0.5 for b, 0.5 is going to take and stretch the wave out. It's going to make the period a bigger number. So if you put in a 0.5 right there, 2 divided by 0.5 gives you 4. So it would stretch it out to be twice as long. So that's how you find the new period of a sine or cosine. So let's try this one. Capital T, I don't know why they use that to represent the period. It's just being consistent with what our book uses and most other books. Okay. So what would be the period of sine 2x? Yep.
Wouldn't the period be pi?
Yes, the period would be pi. The period is not the 2. The 2 is just the b. So you plug in for the b and then simplify. So that would be a shorter cycle, which means the graph is going to compress. Let's look at this one. Cosine 1/3 x. What's going to be the period length for cosine 1/3 x? Yep.
6 pi.
6 pi. That's a small number. It's going to take and stretch the graph out 3 times as much, which means your period is going to be 3 times as long. And how about the last one? Actually, I got 2 more. Sine pi x. What's going to be the period for that one? Yep. 2. that's a graph where we could do it without scaling the x-axis because the period is a nice number. All the other periods have pi. So we're going to want to mark our tick marks like we've done. But this one you wouldn't need to. And how about D? What's going to be the period length there? Yeah. 2 pi over 3. Okay, that's another one that's not nice numbers to deal with, so we're going to want to scale our x-axis to have pi's on it. Okay. So all of these numbers that we just found are basically giving you, if this is your wave, they're giving you the distance from here to here. So they're basically giving you the x value of this coordinate. Right? If you start at 0, the length of the cycle is where the last point is going to be. All right, so we are stretching and compressing along the x-axis. So what is not going to be affected? When we make our table, we do not change the yes. Right, we're not going to change the y's. Unfortunately, the y's are the easy ones to work with. So we're going to have to work with the x's. Okay, and remember the operation that you have. It's multiplication, but everything is backwards when you do horizontal stretching and compressing. So to find the new x values, you are going to divide the originals by b. Now, sometimes you can divide by b. That works fine. But sometimes it's easier to multiply by something instead. Dividing by b would be equivalent to multiplying by what? Yep.
The reciprocal.
The reciprocal. So you can think of it either way, dividing by b or multiplying by 1 over b. It really depends on what the b value is, which way is simpler to think about. That's what you need to do. Let's try an example. All right, so we've got sine of 1/2 x. Again, the way that I'm going to graph these is I'm going to scale my x-axis. So even if a graph is supposed to look really stretched or compressed, it's not going to. Because if I have to scale something 10 times as big, I don't want to use a piece of graph paper 10 times as big. So I'll change my scale. Okay. All right, so Waylon, what's going to stay the same there? Okay, and what are my original y values going to be?
0, 1, 0, -1, 0.
Okay, so 0, 1, 0, -1, 0. And now the original x's. Oops. I'm going to put those off to the side. 0, pi over 2, pi, 3 pi over 2, 2 pi. And what am I going to do to all of those x's to get my new x's? Yeah.
Divide by 1/2 or multiply by 2.
Right. Divide them all by 1/2. Or I think in this way, the easier thing to think about is multiplying them all by 2. Remember, that's a small number. A small number should stretch the graph bigger, make the cycle length longer. And that's what's going to happen. All right. So how about, Michael, what are my new x values going to be?
0, pi, 2 pi, 3 pi, 4 pi.
Yep. And if you see a nice pattern, then you know you probably did it right. 0, 1 pi, 2 pi, 3 pi, 4 pi. Those, because they're all equally spaced, are going to be my labels. 0, pi, 2 pi, 3 pi, 4 pi. Because of how I scaled it, this graph is not going to look stretched because I changed my scale. 0, 1, 0, -1, and 0. Okay, the original graph would have done its full cycle kind of in that space. That's not perfect, but that'd be the idea. We've stretched it twice as much. Okay. Any questions on sketch? We'll try 1 or 2 more, and that'll be it. Cosine 2x. All right, first, what's going to stay the same? Yeah. The y's. And can somebody tell me my y's for cosine? Lynn?
1, 0, -1, 0, 1.
Yep, perfect. Put my original x's off to the side. And what are we going to do to all of those x's to get my new x's? Yeah, divide them by 2 or take half of them. Yep. Whichever way you want to think about it, it's easier for you. That's how we'll do it. Okay, well, if the first one is 0, it's always going to stay 0. Because no matter what you multiply or divide it by, 0 stays 0. Okay. What's half of pi over 2? Yep.
Pi over 4.
So pi over 4. Half of pi is pi over 2. Half of 3 pi over 2 is 3 pi over 4. And half of 2 pi is 1 pi. They don't look equally spaced, but that's because the denominators are all different. If you put them all with the denominator of 4, that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. The next one would be 5 pi over 4, 6 pi over 4, and 7 pi over 4. So they are equally spaced. What's the spacing in degrees? It's pi over 4 is the spacing in radians. But what's that equivalent to in degrees? 45, yep. We have compressed our cycle by a factor of 2. Normally the spacing is 90. Now it's half that. It's a 45 degree spacing. All right. So 0, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. All right. 1, 0, -1, 0, 1. And that's your sketch. Yes?
You forgot the 2 in front of the
Oh.
pile.
2 pi over 4, which I should reduce to pi over 2, but that's okay. Thank you. Okay, question on that one? All right, let's look at the last one. Cosine of pi over 3x. Now that looks like this could be really bad, right? Pi over 3, not a nice number at all in front of x. This is actually going to make the nicest table we've had so far this week. We're going to get very, very nice numbers. Okay, so y's are going to stay the same. 1, 0, -1, 0, 1. Here's our x's. Now, what am I going to do to all those x's?
Divide by pi over 3.
I'm going to divide by pi over 3, or, yeah?
Multiply by 3 over pi.
Yes, let's think of it as multiplying by 3 over pi. Well, first one is going to be 0. What's going to happen in the second one when I multiply?
Pi's cancel.
Pi's cancel, and what am I left with?
3 over 2.
3 over 2. If you write it as a decimal, we can already tell what the spacing is going to be. So it should be going up 1.5 each time. Pi's cancel. What about the next one?
9 over 2 or 4.5.
9 over 2 or 4.5. And the last one?
6.
Pi's cancel. 2 times 3 is 6. Okay, so we get very nice numbers where we don't have to scale anything. We just need to go 1, 2, 3, 4, 5. Need to go to 6. So 0, 1. 1.5, 0. 3, negative 1. 4.5, 0. 6, 1. No labels needed at all because I'm going by 1s on the x, 1s on the y. So again, what looked like could have been kind of a bad problem, it actually makes the table very nice numbers. Okay, and did that stretch or compress the graph? Yeah.
Stretched it, I believe.
What's the period
Oh, wait,
length
no,
on that?
Never mind, you compressed it.
Yeah, what's the period length there?
1 over 6.
6. What's the normal period length as a decimal?
6.2 something.
6.28. So normal period length is 6.28. This one is 6. It's just a little bit of a compression, not much. And that's because this number is just a little bigger than 1. 3.14 divided by 3 is like 1.05, 1.04. Just a little bit bigger than 1. All right. So that is period changes. Okay, so that is the homework. So we'll look at those 8 questions next time. Also, I will make the study guide available probably next period.